So yesterday we were talking in terms of modeling of the turbulent flow. We were principally talking in terms of the flow modeling aspect. Now we are going to change course. We will focus now on the scalar transport, basically on the mixing of scalars. So rest of this course we will focus more on the scalar mixing aspect, because whatever we wanted to discuss in terms of the turbulent flow modeling part, that is already covered. But all the concepts that we actually described during the course of the discussion on turbulent flow modeling will still be required here. So let's say I start with diffusion process. Now, diffusion process certainly plays a very, very important role in reacting flows, but even without any kind of reaction, you know, mixing is actually determined significantly by the diffusion process. So for the time being, if I consider just a scalar transport equation without any kind of chemical reaction. So by now you know the governing equation will look something like this. So let us consider a really, really simple situation. We have a background flow in motion which is moving like this with a velocity u. Q is essentially a point source, and from there some other fluid is issuing from that point. Okay? Effectively, I am not going through the mathematics here, but if you actually go through the governing equation, you will find that the scalar profile will form this kind of mathematical expression. So, which is nothing but a Gaussian distribution. Okay? And the standard deviation in terms of that Gaussian distribution will be given by this. Okay? So, diffusivity, D, plays an important role about the spreading of that scalar. Clear? Look at this one as well. R is basically radial direction from the center of this. So if I consider R divided by U, it gives us an unit. So basically this standard deviation varies as diffusivity times a time scale. Clear? And that feature will be retained in other type of diffusion problems as well. Now, for the time being, if I am considering, rather than a diffusion process, if I consider a transient heat conduction process, you will find that how the thermal disturbance is spreading with time essentially varies as square root of alpha, that is the thermal diffusivity times time. Okay. So if I, instead of having a point source, if I have a line source, you will get this. And width of the plume, as I mentioned, varies as square root of diffusivity times the time.
What is plume?
Plume means essentially is basically issuing, is not very difficult to describe. It's a point source like coming out of something. You can.
Are you referring to the wall?
No, not with it. This is a simple diffusive rate. Now, if I consider a mixing layer x equal to 0, which separates two stagnant fluids. One side you have phi 1, another side phi 2. Okay, these are the two concentrations. Please note at this point previously I did not talk about any turbulent problem. I'm talking about just molecular diffusion. Then one can actually define a normalized scalar in this manner. So in the phi 1 side, this psi is going to take a value of 0 because phi equal to phi 1. In the phi 2 side, it will take a value of 1. I have told stagnant fluids. So if you go back to this equation, this term drops out because there is no velocity. Here, the equation x is 1. The second derivative. So I don't know why it's not coming, but in the updated PDF slide, clearly the equation will come properly. So effectively, once again, the equation solution will take this kind of form. This is essentially how the psi is going to vary. Eta is a normalized distance. Once again, you can see the diffusive thickness varies as square root of d times t. Okay? Now, if I look at scalar dissipation rate, by this time you have seen scalar dissipation rate several times. Defined as the diffusivity times the square of the gradient of the scalar. Okay. So it turns out to be this important thing to notice: scalar dissipation rate has a unit of 1/2. We talked about that before, but you can clearly see here it varies as 1/time. So, couple of things to note. Think about you are putting an ink drop in a beaker of water. What happens when the ink drop falls into the water? That's where the concentration is high. Initially, that's where the concentration gradient will be high, isn't it? And then the diffusion process starts. Basically, concentration, the mixing takes place from the high concentration region to the low concentration region. The concentration gradient will decrease with time. That's consistent with what we observe always, right? Well, so effectively, when concentration gradient is high, by definition, you would expect the scalar dissipation rate to be high. Clear? As it mixes, what happens? The concentration gradient drops. You would expect scalar dissipation rate to drop. So with time, you would expect the scalar dissipation rate to come down. That's what it says, isn't it? As time increases, scalar dissipation rate drops. Important other thing is, for this particular problem, scalar dissipation rate is essentially, it doesn't have any dependence on molecular diffusivity. Why? The diffusion thickness. So when you are basically talking about in one way of what to consider the diffusion dominated region, effectively, you can consider that to be the tube. Basically, the thickness of the tube varies as square root of dt. So here you have d. If you consider length square, that is going to be dt. dt cancels out. But this is important in the sense that you might remember when we talked about the cascading process of turbulent kinetic energy spectrum in the inertial range. We got epsilon, dissipation rate of kinetic energy, u prime cube over L, integral length scale. Several times we actually use that. That has nothing to do with kinematic viscosity. In the similar vein, here, the scalar dissipation rate doesn't ultimately have any diffusivity dependence, at least for this problem. Clear? Now, if I consider a slightly different thing, now I have a slab of width P diffusing into infinite space. I'm telling all of those, if you have actually done transient heat conduction, similar things do exist even for that case, because the diffusion problem without any chemical reaction is identical to transient heat conduction problems without any fluid motion, obviously. So if you are considering transient heat conduction in solids, corresponds to exactly the same thing. Only the difference is replace this by thermal diffusivity. Again, if I have a situation that within that slab psi is equal to 1, outside is 0. So you have a slab in between where you have high concentration, on both sides you don't have anything there. What will happen? It will start to diffuse, right? And that will be given by this. And once again, look at the mixing layer thickness. It scales essentially square root of d times t. The number obviously changes, but that's not the important thing for us. In an order of magnitude sense, the mixing layer thickness varies as square root of d t. If you look at the boundary layer theory, even for boundary layer thickness, it varies as square root of kinematic viscosity times the time. Okay? So what it looks like, this is what you started with. As the time progresses, this is first going to look like this. As the time progresses, the maximum concentration will come down. This will spread, and eventually, this will come down further. The weight will increase, and finally, you will have a constant throughout when it is fully mixed. Clear? You must have seen similar things in real life. But this is the mathematical description for that. If I consider strained mixing layer between two opposed jets, so I have a jet coming here, jet coming from this side, but here I'm bringing some scalar with concentration 1, 0. This is essentially the distribution. Governing equation takes this form. From the potential flow theory, you can actually come to this kind of expression for velocity or counter flow, and then your equation takes this form. Solution again is given by this. Think about this. Velocity has a unit of meter per second, right? Or this is meter. What is the unit of A then? Per second. So scalar dissipation rate turns out to be proportional to A. So A you just told as a unit of 1/second, isn't it? Scalar dissipation rate varies as essentially 1/time. Once again, if you look carefully, there is no diffusivity dependence, the final result. Okay? Look at the denominator, typical thickness of the diffusion layer. I told it varies as d times some time scale. A is inverse of time. So again, it's varying as square root of diffusivity times the time scale. Here, I think we have given enough examples now to actually hammer home the concept that firstly, mixing layer thickness varies as square root of diffusivity times time. Okay? If you don't do the very rigorous mathematical analysis, just think about it. Scalar concentration doesn't have any unit, right? So if I actually scale the gradient of a scalar by some number divided by mixing layer thickness square, then I get something over dt. dt sits in the denominator. That's basically is your gradient square, because mixing layer thickness varies a square root of gt. So if you are mixing, if your concentration gradient square varies as 1 over dt, multiplying with diffusivity with that, the ultimate result is not a function of diffusivity, because diffusivity has been cancelled. It varies as 1 over that. Once again, molecular diffusion. No turbulence here. So far, whatever I'm talking about, just laminar flow. Most of the time, even in one case, I already talked about the quiescent flow. In other words, equivalent to transient heat conduction. Now, I'll come to molecular motion this time, Brownian motion. You must have heard about this. Now, spelling, there's a typo here. Basically, kinetic theory of gas gives rise to this, where rho effectively is density, Cm is molecular, the most probable value of the molecular speed. This is the mean free path. That means the distance between two molecular collisions. Okay? From the kinetic theory of gas, we get this relation. I will move slightly away from what we are discussing for the time being, just to give you an idea. Effectively, from this expression, people originally borrowed the idea of eddy viscosity. If you look carefully, I have, if you divide by density, you will get kinematic viscosity, right? In that case, you will get kinematic viscosity scales as some kind of velocity scale times length scale. Yesterday and the day before, I told kinematic eddy viscosity scales as some kind of turbulent velocity scale times turbulent length scale. Basically, you can see the idea is borrowed from here. Okay? So, now, for gases, generally, Schmidt number is of the order of unity. For air, Schmidt number, Prandtl number, they are of order of unity, roughly 0.7. If you look at your thermodynamic tables, you will see Prandtl number is 0.7 for air. So if they are of the order of unity, diffusivity basically scales like this. There are some extra expressions. If you go for more rigorous molecular dynamic kinetic theory of gases, you will find that. For the time being, please consider I'm talking about kinetic theory of gases. I'm borrowing that concept for all kinds of fluids, but in liquid there are other interactions, okay, which are going to be much more complex, which I'm not going into that, because I'm just interested in developing the concepts. Qualitatively, same concepts are here. So, for molecular chaos, let's say delta X is a mean free path. So, if k jumps take place per unit time, after k jumps, one gets the probability of finding a molecule here, which is given by this. So effectively, this is the random walk. If this is the molecule to begin with, there's a high probability, almost equal probability that it can go either here or there. Clear? If I start with a thing that it can be hit by another molecule and can go either this way or that way. Okay? If these are the constraints, two angles, if I put, just for as a thought experiment. If that happens, this can go either this way or that way. Okay? From here, it can go this way, that way. Similarly, if it is kicked in this direction, it can either come this way or that way. If it goes there, there's a probability that it can come either this way or that way. Now you can see in some places there are more than 2 dots. That doesn't mean 2 molecules are sitting there, and it's basically telling there's higher probability that the molecule can come eventually there. So where will be the highest probability? See here. Because if I have another kick to come here, so effectively it takes the Gaussian distribution given by this. As you go away from here, less probability of finding that. And this is called random walk. Clear? By the way, Einstein's PhD was in fluid mechanics, not on physics. Yes. Okay. So, at least to begin with, Einstein was a fluid dynamist. Now, I'm going to go into a little bit which is close to our known technique. Let's consider a very, very simple thing. F equal to ma. Okay? Let's consider a particle mass m. And it is moving in x direction. So m times acceleration into x dt is the acceleration. So m times a is going to be my net force acting on the particle. This is the drag force. If I am considering Stokes' law, that means Stokes' law where Reynolds number is less than 1. If my particle is small and if I am actually evaluating the Reynolds number based on the diameter of the particle, and that Reynolds number is less than 1, the drag force is given by 6 times mu pi. Here, this is the radius and the velocity. Okay? Those of you who have done this kind of advanced fluid mechanics, you might have heard about Stokes' law. It's essentially the drag coefficient is 24 over R. It comes from there. Okay. One negative sign, drag force is working opposite to the F is some kind of random force, let's say. Okay? It's called Langevin equation, but that's not important for the time being. So probably you can actually understand that from where this equation comes. Okay? If I don't have any kind of random force, this will go zero. Very often people actually use this equation to find out how much the suspension will happen in a fluidized bed in coal power plant. So if you have studied at some point in power engineering or boilers, fluidized bed, you might have actually seen this kind of equation. Now, I'll do some simple mathematical tricks. I'll multiply the whole thing by x. Gives me this. And from there, I can come up with this equation. Okay? So if I actually average that equation over several particles, I will get this expression. And from statistical mechanics, effectively this one is given by half k times t, where kb is nothing but Boltzmann's constant. In the context of continuum mechanics, what we call as temperature, that is nothing but measure of molecular kinetic energy. That's where it comes from. You can see half mv squared. This is nothing but that. Clear? Depends on number of degrees of freedom. Ultimately, this number changes how many degrees of freedom you have. But effectively, this is what you get. For one direction, this is half kb over kb times t. Okay? So I can rewrite my equation in this way. Clear? So if I now actually solve this equation, it will take this form. You can clearly see this is an exponential term. It's actually the actual solution of this ordinary differential equation. You should be able to do it. Okay, based on what you know about differential equations by now. Now you can see this is exponential. Here you have time. So if I consider what happens when time goes to infinity, effectively this contribution goes away. Effectively, I am left with this. And this term, as you can see, essentially plays the role of diffusivity. What I told, that standard definition for those problems varies as diffusivity times time. That's the thickness of the mixing layer. Clear? And that basically is essentially the origin of diffusivity. Well, not origin of diffusivity, but essentially this plays the role of the diffusivity here when you are talking about random walk. Basically, what I have been telling, that the thickness, standard definition of the thickness varies as square root of time. So long diffusion time scale relative to the time scale of the random process essentially is responsible for the diffusion. With that, now we are going into turbulent mixing. All the things that I have mentioned so far, we will need in order to understand turbulent mixing. Just to give you how to actually progress, first we talked about completely laminar behavior, where only the molecular mixing aspect is present. Then we talked about random walk, molecular motion. And essentially now we are putting some kind of irregular motion on top of the thing. We will talk about a very, very famous concept which is called Taylor's quantification of dispersion of fluid particles. So effectively here the particle is a fluid particle. Okay. I talked about the first day that often in fluid mechanics we actually operate in Eulerian frame of reference. That means we concentrate upon a given point and at different times different fluid particles are flowing through that point. This time I'm going to track a given fluid particle. So now I'm actually changing the reference frame. I'm going into Lagrangian frame of reference. Clear? Let's say we will use homogeneous isotropic turbulence, and on top of that I will consider that it is not clearly mentioned, but I will consider as if the turbulence is also frozen. That this is not changing. The particle sees the same, statistically same turbulence, and just as a thought experiment, I am not allowing it to evolve. Let us consider 1D just for simplicity's sake. If you understand conceptually what happens in 1D, you can more or less extrapolate it that what can happen in 3D. X is the displacement, V is the velocity. Clear? Happy with that? Hopefully you can follow it directly. I don't need to explain. Your class 2 mechanics tells you this. If this is the velocity, if you integrate it with respect to time, you will get displacement. Fine. dx dt is, this dx dt is what? So from x of t you get this one, dx dt is v, and that gives you this equation. At the moment, don't bother about the mathematics. I will come back as a tutorial problem. We will actually go through the whole process. So, effectively, for the time being, just for argument's sake, this one, xt square, so square of the displacement, is evolving according to this equation. Here, if I average it, I'm talking about simple Reynolds average kind of thing. So differentiation and averaging commutes. So then I get an average of square of my displacement, and averaging goes into the integral. Okay? This is, in the Lagrangian sense, a correlation function. You have seen similar things, but in terms of spatial sense, when I was talking about the definition of integral length scale. But this time the difference is, previously it was spatially separated, now I'm talking about temporally separated. Clear? So I have a time difference here. And using just that definition, and if I replace this by this one, this one. Fine? Polymicate this one. I will show you this in the tutorial session. So, from that, you actually obtain this double derivative. That can be simplified to this. Clear? Once again, don't bother about the mathematics. Proof will come later in the tutorial. Now, it is extremely difficult to get information experimentally for this autocorrelation in a Lagrangian sense. But let's consider that when tau is 0, tau is the time difference. When the time difference is 0, correlation coefficient is going to be 1 because that's perfectly correlated, isn't it? conceptually, hopefully you can appreciate that that's going to be the case. Because when there is no time difference, essentially it will be perfectly correlated. The velocity at that point is perfectly correlated to the other velocity that we have here. Clear? So essentially these two velocities are going to be perfectly correlated if time difference is 0. If time difference goes to infinity, what will you consider? What will happen to the correlation coefficient? It will go to 0, right? It will become uncorrelated if I actually wait for a very long time. So 1 is for tau equal to 0. When tau goes to infinity, correlation goes to 0. Happy? Now consider when time we put this one to be 0, sorry, this one to be 1, okay? Effectively, this one varies as v square, t square. Here, if one uses effectively the concept that I discussed earlier, the standard deviation of thickness varies as diffusivity times time. So if we actually compare this, you can see this one plays the role of turbulent diffusivity. There, one important thing, it's not a constant. So, moreover, you can see this basically depends on time as well. So, for short term mixing, turbulent diffusivity is not constant. Clear? Happy? About that, for large time interval, effectively, this is what you are going to get. For large time interval, that if you, this is the Lagrangian time scale, and that basically gives you this. Again, if you actually compare that with this result, then you will get this relation. Okay? So if I consider this v square is equivalent to u prime square, let's say, u prime square times some kind of turbulent time scale gives you scales with integral length scale of turbulence. So then turbulent diffusivity scales as u prime, that's the RMS velocity fluctuation, and the integral length scale. In last couple of days, essentially, I told that any kinematic viscosity scales with this. Now I am telling for long time interval, turbulent diffusivity scales like this as well. Okay? So that's why the turbulent Prandtl number or turbulent Schmidt number are generally considered of the order of V, because kinematic eddy viscosity or turbulent diffusivity both scale with u prime times. Yeah. But that's for the long time interval. Clear? So behavior firstly is very different for short time and long time. Clear? So long time turbulent mixing is qualitatively similar to molecular mixing. In the molecular mixing, what we saw, effectively, the diffusivity is not a function of time, but turbulent does not, diffusivity does not remain constant, it is and dependent on time for short term mixing. And if you use standard eddy diffusivity concepts, then you may not be able to capture the short-term mixing. So if you have a nozzle from where something is injected in your domain, and you are using eddy diffusivity concept, basically put whatever turbulent Prandtl number, turbulent Schmidt number, and if you are trying to find out the mixing pattern very close to the nozzle, doesn't matter what Prandtl number or turbulent Prandtl number or turbulent Schmidt number you are using, you may not get the correct result. And if you get the correct result, that it might be for wrong reasons. Okay? Far away from the nozzle, then we actually go back to the long-term behavior, then long-time behavior, then it can actually capture the behavior perhaps. Okay? Now, just for the sake of gaining a little bit of insight, I already told it is extremely difficult to get this autocorrelation. If I approximate this by this kind of distribution, basically it follows the asymptotic behaviors. At times, if I put tau equal to 0, you get r tau equal to 1. If I put tau equal to infinity, this goes to 0. And if I put that in this expression, I'll end up with this. And effectively, this one captures both short-term and long-term behavior, and generally remains qualitatively consistent in terms of the experiments. However, please understand, this is a very important thing. This TL sitting there is determined like this. It's a Lagrangian time scale, integral time scale. That's not same as large eddy turnover time. But generally, we actually model it. Model means approximation. Approximate it to be proportional to the large eddy turnover time. This constant obviously is not a constant, it's a parameter, varies between this. Quite a wide variation. It's very, very flow dependent.
So eddy turnover time is the time taken by eddy to break down into.
Yes. Generally, integral length scale divided by the RMS velocity fluctuation, that's essentially your eddy turnover time. If you consider the tutorial problem that we had, I think it was day before yesterday, I think, where I was talking about every eddy breaks down to half of its size and carries on. You saw the whole time it takes to actually come to that stage. Scales with integral eddy turnover time. So, in some ways, you can also consider about the time taken to actually finish the full cascading process. Now, if we now look at the actual variance of phi, this time I am writing the equation for compressible flow, just for completeness sake. So, in the case of Reynolds averaging and without any kind of density variation, it will look like rho I prime square. Okay, rho is obviously constant, so it will come out. I prime square is nothing but variance. You will have these terms. Obviously, this is the transient term. This is the advection term, mean advection term. This is turbulent transport. The term that you are seeing within the parenthesis is actually scalar flux of variance. Variance is also a scalar. So it sounds a bit odd, but it's a scalar flux of variance. Okay? This one is often responsible for generation of scalar variance because of the mean species gradient, mean scalar gradient. You can see the mean scalar gradient sitting there, gradient of mean. Okay, but there is no compulsion; it will always generate. It can actually kill as well. But I'll explain later. If you have gradient type transport, this one generates. If you have counter gradient transport, we talked about counter gradient behavior yesterday when we are talking about the Reynolds stress. It can happen when heat release effects dominate over turbulence effects. But if you're thinking about a situation where gradient transport happens, then this term always generates scalar variance. It's a positive term. Okay? These two are not source of sink. They just redistribute. This can generate. This one is a generation term because of the chemical reaction. Okay? And this one especially have a negative sign. Epsilon is given by this. This is a positive term. We talked about that in one of the tutorial problems. Showed it that it's going to be principally positive under every circumstance. That's our scalar dissipation. Basically, more appropriately is the unresolved part or the fluctuating part of the scalar dissipation rate. You might remember I gave the analogy of putting sugar in your coffee cup or tea cup. So when you actually stir it, you are actually inducing scalar gradient. This one starts to generate. Obviously your tea cup or coffee cup, there is no chemical reaction to it. This term goes to zero. If you have suddenly chemical reaction happening in your tea cup or coffee cup, you are in trouble. So hopefully that doesn't happen. This one is responsible for killing any kind of scalar fluctuation. This one actually is responsible to produce a homogeneous mixture what you treat ultimately. Mostly the behavior until very recently was studied for passive scalar mixing, that is without any chemical reaction, or in the case of non-premix planes. Some people, including me recently, concentrated a lot on the modeling of scalar dissipation rate for reactive systems. I'll talk about that later in the third lecture. But those materials are really, really new. There are review papers for that in 2011. People have started to use that in an industrial context, but it's relatively new. Has not fully become a textbook material yet. It's well established in the literature, but I think just to mention that scalar dissipation rate, we have already talked about, it has a unit of 1 upon time. It gives you the rate of micromixing. What I mean by micromixing, if I consider a field, mixing field, the mean concentration might be same everywhere, but fluctuations may exist on top of that. Here, this one is responsible for killing the fluctuations. So if you have a system where there is no fluctuation, there is a completely micro-mixed state. Here, it also appears in the entropy generation transport equation. So yes. So mixing is an irreversible process, and that will lead to entropy generation. It will actually appear explicitly in the entropy generation transport equation. There are about 3 papers by me on that, how you can actually relate this to the entropy generation transport equation. For isotropic homogeneous isothermal turbulence, you can actually write it in this manner. This is the variance. This one L5 is the Taylor microscale for mixing. We talked about Taylor microscale. Any fluctuating basically gradient of any fluctuating quantities can be scaled with respect to the microscale. That I mentioned, but at that time I was talking in terms of the velocity fluctuation. This Taylor microscale for mixing for scalar can be different from the Taylor microscale for velocity fluctuation. Okay? Now, for passive scalar mixing, scalar dissipation rate is often modeled like this. Variance doesn't have any unit, but scalar dissipation rate has a unit of 1 upon time, right? We told. Time scale for mixing. And how the time scale is actually considered? Like this. C5 is a modeling parameter. L over U prime. Once again, that any turnover time. If I write L over U prime in terms of K and epsilon, I will get K over epsilon. Clear? And that effectively is this model, where C5 is a model parameter generally taken of the order of 1, order of unity. Okay? Couple of things. This is called linear relaxation model, because effectively you are giving a time scale, and actually if you consider a linear system for control, it is basically trying to actually bring the variance to 0. So it's basically trying to bring your system to a micro mix state, nothing else. It's not strictly valid for premix. Under certain circumstances it works, but in general it is not valid. We'll talk a little bit more later. One other thing to actually note, this is a model for mixing purpose, right? But see which are the input parameters, K and epsilon. So if you are solving model transport equation for K and epsilon, isn't it? So effectively, if you are doing a RANS calculation, your K and epsilon value come from essentially from solving K equation and epsilon equation. There are approximations involved in those equations. So if your K value and epsilon value are not fully accurate, that also affects the performance of this model. Okay? This is an example where inaccuracies to the input parameters can also affect the model performance. Clear? In the case of premixed flame, micromixing between the cold unburned reactants and hot burned products, this is essential to sustain the chemical reaction. Okay. And if you consider Reynolds average reaction rate of the reaction progress variable, you remember I told you you can define a reaction progress variable based on either a reactant mass fraction or a product mass fraction such that reaction progress variable takes a value of 0 in the unburned gas and unity in the fully burned gas. So it's a kind of a reduced species mass fraction. So it's given by this, in other words, mean reaction rate is directly proportional to the scalar dissipation rate. Higher the scalar dissipation rate, you get higher reaction rate as well. So that's why it is such an important term in the mixing as well as the reacting literature. So if I consider, let's say this is my initial distribution. Let's go back. The mean value is 1, but I have actually, this is the PDF of scalar phi as a bimodal distribution. This is a Gaussian distribution. Mean scalar dissipation rate is given by this. This is the RMS value. This is the scalar microscale, as I said. T is the diffusivity. You can actually appreciate, depending on, this is some kind of reference length scale, so don't worry about it, but just look at these things. LF value does not change, but if you change L5, the distribution will look different. When L5 increases, you are seeing bigger blobs. Okay? This is where the distribution is bimodal in nature. That means you have one value and another value in between the samples are there, and this one when it is Gaussian. Okay? So right at the beginning I told if you have a point source and it's giving out the scalar, then you will have a Gaussian distribution. If they are completely separated from each other, then you will have bimodal distribution. Evaluation of the mixing process, bimodal. And if forget about, for the time being, I have taken it from one of my simulations. What PSP is not important for the time being. Just consider that as the time progresses, what happens. So if you start with bimodal distribution, with time, so it has a mean value of around 0.8. As time progresses, eventually it will give rise to a Gaussian distribution. Eventually. So we started with this Gaussian distribution as an initial condition. It's basically in those boxes that I showed you, then you actually allow them to evolve under turbulent condition, under homogeneous isotropic turbulence. What happens? The Gaussian distribution remains Gaussian, but the peak goes up, the PDF becomes narrow. Why? As the mixing progresses, ultimately you are going to get a delta function, because everywhere the concentration will become the same for both cases. Clear? Phi prime. How it evolves with time. Once again, forget about ESP, understands what happens with time. If I have small value of the scalar microscale, couple of slides back and it is written like this, that smaller value means higher scalar dissipation rate. See, it decays faster. Clear? The larger the value is, it actually takes more time to come to a zero value. Zero value means it's completely micro-mixed. Understood? The effect of leg scale distribution. The extent of mixing is often quantified by this. It's called segregation factor. This is the variance divided by this. This is the maximum possible value of the variance that you can get. Okay? You get these values only for bimodal distribution when they are completely segregated from each other. Here, if you look carefully, here the broken ones are Gaussian, bimodals are the solid ones. So keep that in mind, that the Gaussian ones, the broken ones, actually showed a more rapid decay than the bimodal ones. So G1 means it is completely unmixed. G equal to 0 means fully micromixed. Okay? Under fully micromixed state, this one will go to 0. Variance will go to 0. So, with that, let us stop for the first lecture. We introduce the fundamental principles of mixing. Diffusion layer thickness varies in the molecular mixing, varies as square root of D diffusivity times time. That behavior is consistent with long-term mixing behavior under turbulence, but short-term behavior might be different. Okay? We talked about the role scalar dissipation rate plays under turbulent mixing. The mixing plays a very, very important role for reacting flows like turbulent, premixed flame, non-premixed flame.